we'll get started with our lab. We are jumping again. Our lab is a week or so ahead of our lecture. What we are trying to learn about is Faradays Law. And the idea there is that a changing magnetic flux through a coil of wire induces an electric potential, an EMF, in that coil of wire. So let's take a look at a couple of examples. We've got a coil of wire hooked up to no batteries, just hooked up to an ammeter. And my coil of wire is perpendicular to the page. And I've got a magnet here. And I move that magnet toward the coil of wire. Like this. Got my coil of wire. I move it toward the coil of wire. And while that magnet is moving toward the coil of wire, I get a current flowing. Right? There's no battery. There's no battery in the circuit, just a loop of wire hooked up to an ammeter. But when I move that magnet toward the coil of wire, current flows. If I stop moving it, I've got my ammeter here. Got my loop of wire perpendicular to the page, and my magnet just sitting here. What happens? No current. And if I move my magnet away, it's my ammeter, my current loop. If I move it away, I get current in the opposite direction. Okay, it's a little strange, right? When is the magnetic flux at its greatest? Okay, I've got my coil of wire here. Got my magnet. And if I move the magnet, as I said, if I move the magnet toward the coil of wire, we get current to flow in there. If I just hold it close, so the magnetic field is the strongest through the coil of wire at that point, just hold it there, nothing happens. No current in my loop. If I pull it away, we get current again flowing. So what matters is how the magnetic flux through the loop of wire, how it's changing. It starts out with my magnet far away. There's very little flux, magnetic flux through the loop of wire, right? Because the magnetic field is spreading out. It's very weak by the time it gets to the loop of wire. But I move it closer and closer and closer, and the magnetic flux through this loop of wire gets bigger and bigger and bigger. And as it gets bigger, we get current. We get an induced EMF. We get an induced potential in the loop. Current flows. But if I hold it there, just a really strong magnetic field right there, nothing happens. If I pull it away and the field gets weaker and weaker and weaker through the area that is defined by the loop of wire, current flows again. Faraday's law tells us how that potential, how we can calculate that potential. The induced EMF is equal to negative the change in magnetic flux with respect to time. That's for a single loop of wire. Normally we would have multiple loops, so we could write that as minus n. Where n is the number of loops or turns. And remember what flux is? It's the integral of B dot dA. This is magnetic flux. We did a lot with Gauss's law with electric flux, right? The flux, the amount of electric field penetrating a certain area was the integral of E dot dA. Now we're doing it with magnetic field, magnetic flux. It's the integral of B dot dA. If B is uniform over the area, then this is just B times the area times the cosine of the angle between them, right, when you put their tails together. But if B is not uniform over the area, you have to integrate to find the magnetic flux. And just a quick review, what can cause the magnetic flux to change? B, right? Changing the magnetic field strength can cause the magnetic flux to change. So that's what my example was here. When I moved the magnet closer to the coil of wire, I was increasing the strength of the magnetic field in the region of the area defined by the loop of wire. So I increased B. That caused the magnetic flux to increase. I moved the magnet away. I decreased the magnetic field there. That caused the magnetic flux to decrease. What else could I change? I could change the area, right? Let's see. It's a little hard with that one, but it is possible. I could make a loop of wire out of something like this. In the first case, I'm going to repeat what I just said so that I can capture it on video for everybody else. In the first case here, I'm moving the magnet closer and closer and closer to the loop of wire. What's that doing? That's making the magnetic field in this region, the region defined by the loop of wire, stronger and stronger and stronger. I'm increasing B. I'm increasing the magnetic flux through that loop by bringing the magnet closer to it. Or by bringing the magnet away, I'm decreasing the strength of the magnetic field here. I'm decreasing the flux through the loop. Or that's one knob I have for changing the flux, changing the magnetic field. Another knob I have for changing the flux is changing the area. So if I have a loop of wire that's shaped like this, the area is fairly large, but if I just pull on the ends, what have I just done? I've just made the area very small. Now the area is big, now the area is small. So I can, if the wires are flexible like this, it's easy to, you can see how I can change the shape and change the area. So that's another knob I have. And what's the third knob I have? The orientation between the two, right? Because it's a dot product, B dot dA. So my loop of wire and my magnet, I get the maximum flux when they're perpendicular like this. But if I rotate my loop of wire, If I rotate my loop of wire, you can see the magnetic flux gets less and less and less. And when it's aligned with my magnet like this, I have zero flux. None of the magnetic field from my magnet penetrates the area defined by my loop of wire when I have it like this. But as I rotate it, then I get maximum flux here and minimum flux here, zero here. You can see how that works, right? So changing the orientation will also affect this. So increasing or decreasing the magnetic field strength, increasing or decreasing the area. Let me go back to my... So increasing or decreasing the magnetic field strength is one tool we have for changing the flux. Increasing or decreasing the area of the loop, the area that the wire defines, is another way. And the third is the orientation, changing the orientation between the two. Question about the magnetic flux. Yeah, so here's my coil of wire. I'm just going to draw it perpendicular to the page like this, right? That's my loop of wire. And here's my magnet. So let's draw the magnetic field lines from this magnet. They come out like this. Right? So very little, only one magnetic field line penetrating that loop of wire. Very little flux. But I bring my magnet closer. And I've got my magnetic field lines look like this, right? Now look how many magnetic field lines penetrate the area defined by that loop. The flux has gone way up. So this is maybe it's a little hard thing to accept, but it all comes from the fact that we have already talked a lot about the fact that charged particles moving in a uniform magnetic field will feel a force, right, because of the interaction with that field. Well, the particle doesn't really care whether the field is stationary and the particle is moving, or the particle is stationary and the field is changing, right? Either way should produce a similar effect. So if we think about this, it may not be as surprising then that changing the magnetic field would exert forces on particles that cause them, charged particles like electrons, that cause them to start moving. And they act as a current then when they move in a wire. That's another way of thinking about it if you prefer. When the magnet is moving toward the wire, when our flux is increasing, the current gets set up in such a way that it opposes the change. The current always opposes the changing magnetic field that creates it. If the magnetic field is increasing, so we're moving the magnet closer to the coil of wire, and the magnetic field is increasing in strength there, then the wire, the current in the wire is going to go counterclockwise. And the reason is that it also produces its own magnetic field, right? A current carrying wire fills the space around it with a magnetic field. And the magnetic flux that it creates has to oppose the change that caused the current to start moving to begin with, or we'd have a violation of our conservation of energy. In other words, let's think about what would happen if the current went the other way. We've got a magnetic field through our coil of wire. We start increasing the magnetic field. Let's pretend a current gets set up in this direction. That current creates its own magnetic field. What direction? It forms a circle around it, right? We put our thumb in the direction of the current, and inside of the loop, it would be into the page. Do you see that? If we have a loop of wire, and we have a current flowing, let's say the current is flowing this way, that would be clockwise as you look at it, right? If the current's flowing this way, we know that the current forms a little circle around that wire, right? Circles around that wire. The question is, are they going that way or are they going this way? So we put our thumb in the direction of the current, and our thumb says that as you look at it, the magnetic field points away from the camera or toward me through this loop of wire, right? Into the page, if we were looking down at a page, right? Into the page. We had a magnetic field here. We pointed toward me, away from the camera, toward me, into the page. That's the way I drew it, into the page. We increased the strength of it, which if it caused current to go this way, the current then would be adding more magnetic field into the page. What does magnetic field into the page do? Create current, which creates more magnetic field into the page, which creates more current. We'd have free energy. We would just have to turn on a little magnetic field to get some current flowing, and then we could turn it off because its own magnetic field would cause more current, would cause more magnetic field, would cause more current. It violates conservation of energy. We know that we're not going to get free energy from this, right? Let's think about what happens if we do it the opposite direction. We turn on a magnetic field toward me, into the page, away from the camera. And let's pretend the current goes the other way. That means that its magnetic field through, all we care about is what's happening in the interior of the loop. We don't care about what's happening outside. The magnetic field from this current that just started up points toward the camera, away from me, out of the page. But it takes a current into the page to get the current to flow. So it's fighting itself, which makes sense. You'd have to put more energy in. You'd have to change the magnetic field some more to get the current to keep flowing. And you'd have to change the magnetic field more to get the current to keep flowing. You don't get something for nothing. So at least that makes sense with conservation of energy. So now we know that the direction of the current has to oppose the change. Its magnetic field that it creates has to oppose the changing magnetic field that created the current to begin with. If B is increasing, current is going to get set up in the counterclockwise. It opposes the change in flux that created I. It doesn't oppose the magnetic field. Sometimes it adds to the field, sometimes it subtracts from the field. In this case, it's subtracting because the field is getting stronger and stronger and stronger into the page. The current has to create a field that opposes that subtracts from it, tries to make it weaker, get you back to the starting point. But if the field was getting weaker, then the current would add to it. It opposes the change. It would try to increase the flux through the loop. Because the field through the loop was getting weaker, it would try to add to it to get back to its starting point. It opposes the change, not the field. All right, so one more thing we need to talk about before we can do the lab. If we have a magnet and we drop it toward a loop of wire, got a loop of wire, got a magnet, and we're dropping the magnet down toward the loop of wire. That's what we're going to do in this week's lab. The magnetic field strength is getting stronger and stronger and stronger through the wire as the magnet approaches the loop of wire. So a current gets set up to try to oppose that, to make its own magnetic field up, to decrease the change. That means that the current is going to flow out on this side and in on that side. The field from the magnet is doing this. So the current is going to try to create its own field that points up. You follow? Good question. Will it slow down? The magnet is creating its field, and that loop of wire sort of looks like a magnet, doesn't it? With a north up and a south down. It creates the same magnetic field. We'll talk more about that. What do? They repel. So the motion of that magnet is slowed down as it falls toward the loop of wire. Now it passes through the loop of wire. The magnet comes along, passes through the loop of wire, and continues falling below it. So here's my loop of wire, and here's my magnet. So the field is still pointing down due to that magnet, still points down, but now it's getting, instead of getting stronger as the magnet came closer to the loop, now after it passes through, it's getting weaker and weaker and weaker. So the current gets set up to add its own magnetic field. The current has to come out on this side and go in on this side, so it adds to it because it doesn't like the change. It started out, it had a big magnetic flux down when the magnet was close, and as the magnet moves farther and farther away, it's getting weaker and weaker, so the current gets set up to try to add it. It wants to keep it big. It tries to get back to its starting point. So what happened in here? The current changed direction as the magnet passed through the loop. It was in one direction for half the time, and then it goes in the other direction. All right. Let's take a look at this week's lab. So what we will do, and I haven't posted anything yet because I'm not finished. I'll hopefully get it finished by 4 o'clock by our office hour and get it posted. But I'm still working on the instructions for how to do the analysis. But we'll talk about it. What I have set up is a coil of wire. Actually, it's a lot of coils of wire. The wire goes around and around this spool here quite a few times. And it comes off and it's hooked up to an oscilloscope. And then we have a string running through it, and we have a magnet down here that has a hole in the center. So the magnet can move along that string nice and easily, and the string guides it so it goes right through our coil of wire. It would be hard to drop it, so it goes right through that coil of wire every time. So the string is just there to guide it through the coil of wire. So I've done the experiment. I've dropped the magnet through the coil of wire, and I use the oscilloscope, and the oscilloscope gives me an image that looks something like this. This is the electric potential versus time. As the magnet approaches the coil of wire, we get a potential, in this case, in the negative direction, but don't worry about the sign. If I just switched the leads, it would have been positive. What's important is that it starts out in one direction. In this case, it happens to start out in the negative direction. And it hits some large value. And then the magnet passes through the loop. And as it goes through, remember, the current has to switch direction. That means that the electric potential has to switch to push the current in the opposite direction. And the current goes in the opposite direction. The potential changes sign. It doesn't matter whether it starts positive and goes negative or starts negative and goes positive. That's irrelevant. You just change the leads on your oscilloscope. But what's important is the shape and the fact that it changes signs like that when you go through. So I did this a number of times. I dropped it from different heights, the magnet from different heights. And the oscilloscope, you can output the data. It collected, I forgot how many, 1,500 or 2,000 data points over this very small region of time. And it recorded this. And I downloaded that file. It's called a CSV, a comma separated value file. And all spreadsheet programs are designed so they can open comma separated value files. It's basically a text file where all the data has a comma between it, comma separated values. And then when you open that into Excel or into Google Sheets, it will either recognize that it's a CSV file, or you tell it commas are used to separate the values, and it imports all those into different cells in your spreadsheet, and then you can graph it and manipulate it and do all kinds of interesting things with it. So I did the first part for you. You watch the video, that part's done. And then you'll do some analysis. And so let's talk about the analysis now. The first thing we want to do, there's two main things we're looking at in this. Before we talk about this, one more thing. What happens now? The magnet has completely gone through the loop. It's falling. It looks like this. What does my loop look like? My loop also looks like a magnet. But it's switched now. Remember, as the magnet approached the loop looked like a magnet with a north pole up. But now the current has switched. Now it looks like a loop with a north pole down. What do these do? Here, they repelled, which slowed the falling magnet. Here, what do? They attract. But what does it do to the falling magnet? It slows it down. It always slows it down, because if it caused it to go faster, we'd be violating our conservation of energy. We would just give it a little push, and the forces that are generated would cause it to go faster, and then that would give it more force and cause it to go faster and give it more force. It would violate our conservation of energy. We always get this repulsive nature. We always get things where if we generate energy, it would cause our object to slow down. We have to put more energy in if we want to keep generating the energy. You don't get something for free. Okay, two things we want to look at in this lab. The most important one is that the induced EMF, the maximum induced EMF, is proportional to the rate of change of the flux. We're taking a magnet and we're dropping it through a coil of wire. And we're going to get some kind of signal. I'll call that the peak-to-peak EMF. We'll just say that's sort of the maximum amount that's generated. Now, if I could get the flux to change at a faster rate, if the flux is changing slowly, if d flux dt is a small amount, you get this. If the flux is changing at a faster rate, then you get a bigger peak-to-peak value. You see that? Because the EMF is proportional to the rate of change of the flux. Well, how can we get the flux to change at a faster rate? We make our magnet go faster through the loop, right? You see that? We just make the magnet go through the loop faster. Well, how do we do that? We drop it from a higher height. So the first thing you're going to do is look at the data. We're going to compare, you're going to plot the EMF, the peak-to-peak EMF, right? The peak-to-peak, that total generated EMF, versus the velocity of the magnet, because the velocity of the magnet is proportional to d flux dt. And we are hoping, what are we hoping for? A linear relationship, right? Because they should be proportional. According to Faraday's law, they're proportional to each other. The change of flux with respect to time, which is proportional to the velocity, is proportional to the EMF induced. And we're just looking at peak to peak. That's the maximum induced. So that's the first thing you're going to do. The second thing we're going to do, let's look at this equation one more time. Let's forget about the n and the minus sign. We don't care right now. What we care about is, let's move the dt to the other side. And we'll integrate this. And what do we get on this side? the integral of E dt, the integral of the flux, the EMF, this is, these plots we're looking at, it's EMF versus time, right? What is the integral of EMF versus time on an EMF versus time plot? The area under the curve, right? The area under the curve. So this is area. If we have a plot that looks like this, the area is that right there, right? And the change in flux, so let's think about that. What is the change in flux? We have a magnet that produces a certain strength magnetic field right at the front of the magnet. If we start with that magnet way up high away from the loop, what's the magnetic flux through the loop? 0? Close to 0? Probably about 0, right? Then the magnet drops, and it doesn't matter if it drops from a close distance or a big distance. Eventually, the tip of that magnet is right over our coil of wire, and we have all of the flux from that magnet going through the coil of wire. So as long as we start from a high enough point, right? If we start too low, you start out with some initial magnetic flux, and then it goes to maximum. But if you start high enough, like 25, 30 centimeters above, then the initial flux is basically 0. It doesn't matter how high you start, as long as you have enough distance for that first one. As you go higher, it doesn't get any weaker. It's pretty much 0. And it doesn't matter where you start. At the end, you're going to be at the maximum value. So this is fixed. This is the same for all of them. So if we plot this, the area under the curve, versus our height, or our velocity, or whatever you want to plot it against, then we should get no change, right? We should get a horizontal line. It should be the same for all of them. Now, there's some noise in the data. It ain't perfect, let's just say that. But I think you'll kind of see that it's leaning in that direction. The only tricky part here is that some of this area is negative, and some of this area is positive, and so we need to take the absolute value in order to do that. Because we want we don't want the fact that it changed direction. We just want the total area. We need to take the absolute value of this. Otherwise, we'd get 0, right? We don't want that. So there's a trick for doing that in Excel. It's not easy, but there's a trick for doing it. I'm sure it'll work in Google Sheets also. Okay, should we look at a couple of Excel or Google Sheets tricks? So the first thing is to find the peak-to-peak value. Well, you've got a file filled with data like, I don't know, 1,000, 1,500, 2,000 data points. I forgot exactly how many there are. A lot of data points. You know, I guess you could scan through and try to find the maximum value and the minimum value. But these spreadsheets have functions that tell you. So you set one of the cells equal to, do I want to go to Excel? I think I'll just write it here. You in your spreadsheet program, max, and then you select your cells. So let's say your data, one more thing about the data, and again, I'll make a video of this, but you're going to have columns, right? Column A will be time, and it's the same for all of them. This will be V1, V2, V3, and these are based on how high you fall, right? So I guess maybe I shouldn't say V. Maybe I should say 30 centimeters, 40 centimeters, something like that, right? 50 centimeters. Anyway, you get the idea. You're going to get these columns. Time is the same for all of them because of the way the trigger was set up, and the time spans were all identical. So this is you're going to open up a file, and it should be in this kind of have this look to it. Then down here under column B, you put an equal sign, max, B, whatever the first one is. Is this 1 or whatever the first? I don't know how many you have, but let's say the first one is in row 1, B1 to B. Let's say the last one is in 1400. I don't remember exactly where it is, but you can look on your spreadsheet. And this, hit enter, and it tells you what the maximum value was in that whole region. Then in the next cell, you say minimum. And it tells you what the minimum value is, and then you take the difference and you get the peak-to-peak voltage. So you don't have to go looking through 1400 or whatever, 1500, 1600, 2000. I don't remember how many data runs there are. I think there's about that many. You don't have to go looking through all of them. Have Excel find it. And then you do the same thing for every column. You can copy these over. So in the next column over, it will be this one will be C1 to C1400, right? And the next one over will be D, right? D1 to D1400, and so on. Copy them over, it does it for you. Now the tricky part, so that gives you your peak to peak. So you get one data point here, right? This is one data point for each column. So you get a peak to peak for 30 centimeters, a peak to peak for this column, a peak to peak for this column. I forgot how many columns there are, 6, I think. You get 5 data points, and you're going to plot 5 data points on a graph like this. 1, 2, 3, 4, 5, and you'll fit a line and look at the R squared, do a linear fit, and look at the R squared value and see how good a fit it is. Hopefully it's 0.96 or better, 0.97. I think it's around there. One of the main problems I had when I was doing this is that my data is very noisy, and I think that was a problem. I don't know what was causing the noise. I changed everything. I changed the coil that I was dropping the magnet through. I changed each of my cords, my cables, one at a time. I changed the input from 1 to 2 on the oscilloscope. The only thing I didn't change is the oscilloscope because I only brought one oscilloscope home with me, so I couldn't change that. I changed everything, and it was getting a very noisy signal. Usually we get a pretty clean signal. If you look at the drawing or the image in the lab write-up, it shows a nice thin line. And then if you look at the images that you're going to plot, they're very fuzzy. There's a lot of noise, and I think that, I don't know what caused it, but I tried everything, and I think that contributed to some of the problems. I think, so you're going to get something, 0.96, 0.97, something like that for your R squared value. Typically, we would get a little bit better than that on this first part. Okay. Then for the next part, you're going to do follow the instructions in the write-up. But what we're going to do is you've got a signal that looks like this, right? I'll just draw it like this. And we want to come up with the area, right? A kind of a quick and dirty approximation of the area under this curve using Excel. Well, in Excel, we can take the time we can take the time interval here from one data point to the next and multiply it by our value. This is E, right? So E times dt, or delta, I guess I'm calling it delta t. We're multiplying E times delta t to get the area of one of these segments, right? And we want to add them all up. But all the delta t's are the same. So do we really need to multiply by delta t? I say no, right? Because we're just looking for a proportionality in the end, right? Is this constant or is it changing over as we change the height? So instead of multiplying E times delta t, since the delta t's are all the same for 30 centimeters, 40 centimeters, 50 centimeters, 60 centimeters, they're all the same delta t's, let's just add up all the e's. So we wanted to sum all of these, right? But what we're going to do is just sum the e's. It's proportional, okay? Because the delta t's are all the same for all of them. And how do we, and you in the worksheet it says you can use this sum if. I assume that Google Sheets has a similar function. This is in Excel. Sum if, and then you tell it if the value is greater than 0, you add them up. And then if the value is less than 0, you subtract them. So you're subtracting a negative. It's like taking an absolute value. So follow the instructions in the write-up on using the sum if, and then you're going to compare that value. You're going to whatever you add up here, this is going to be your area basically, or it's proportional to it's kind of the proportional to the area, and you're going to take that value and plot it versus height, and hopefully get aligned. It's going to be all over the place, but you're going to do a linear fit. And you're going to look at the slope and see how close it is to 0. It's pretty small. I think it's less than 5, and the numbers here are like 750 or something. So that's a pretty small slope, but the numbers are all over the place. It's not the best data set. It kind of points you in the right direction, but there's a lot of noise. It's the best I could do.